Hey Pixelers, Michael Haddon here. Now, one of the things I keep finding is when people think of security, what they typically think of is adding a tool, right? You add a tool to add security. But very rarely is that actually how you're meant to make your application secure. Usually, the way you make things secure is by understanding them. And so today, let's take a step back and have a look exactly what are containers and how do you actually make them. Now, this isn't going to be a video literally explaining what containers are. I'll do a brief overview very shortly, but it's really looking at a container and really going, hey, what makes this thing work? What is a container? What's inside of a container? And what is actually essential to actually deploy my application? And so what I'm thinking of doing is let's go through some example containers and let's see what we can do to make them more secure. So we can learn a few things together and hopefully you'll learn some techniques that you can apply into your own projects. So first things first, let's have a look at a Node.js project. This is a Nuxt project. It comes from one of the official Nuxt example projects. And if I install the dependencies and run the project, we can just get a quick idea of what actually this does. So npm run dev and wait for the server to start. So this is just an example project, so we can see it here running a web server. Now, before we get stuck into the details, let's just containerize our first application together. And we're going to do this how, you see most people write their first Docker file. So just to remind you, the way that Docker works is, you build from a base image and you run commands in that to be able to build your release that you deploy that runs your application. We're going to build our container from the basic node image. Let's say we have a work directory that we want to define. Now, just to keep it simple, we're going to copy in all of the files in this directory into the container. And just like we did locally, we're going to install with npm. And then we're going to run the npm build command so we can actually build this deployment. Now, all we have to do is just specify the compiled JavaScript output that we want to execute. So output server index.mjs. So this is a very basic Docker file. And when we run this, docker build, we're going to call it one nuxt1, specify this directory. Now this is obviously going to take a moment, it has to download any sort of base image that it needs and rerun the npm install command. And now it's built, we should be now able to run our container and actually access, I think it's on port 3000. And now we should be able to access the same server from within the container. Wonderful. So we've just made our first container. And so just to remind you what this does, we're specifying here that this comes from a base image. We're setting a work directory, which is where we're going to install application to inside of this image. We're copying over all of the files, making sure we have all of the dependencies up to date. We're building it, and we're now executing our JavaScript compiled output. So that's a very simple container. You can go to production with this and everything would work in theory, but it's horrible. And let me show you why it's horrible. So let's do Docker images. So we're going to see here all of the images we have built. And if we see here for one nuxt1, we can see is 1.8 gigabytes. How did that happen? That's 2 gigabytes. That's ridiculous. If I want to deploy this onto my server, it's going to have to download 2 gigabytes to deploy it. If I'm going to have this in my CI/CD pipeline, it's going to be having to pull all of this rubbish every single time it's going to be doing a release, and I'm going to have to be pushing 2 gigabytes of data to my registry. Now, you may not realize how ridiculous that is. So let's go inside of our container. So it's still running in the background, and I can do docker exec. Now, if I do du.h, I'm going to get the size of this folder in a human readable format. And we can see that my application is only taking up 367 megabytes. So how is it, just to remind you, that we're on nearly 2 gigabytes when my thing is only 367 megabytes? Now, you may be a bit confused here. What's this got to do with security, right? I thought we were talking about security, and now you're talking to me about file sizes. Well, this is the basis of how to build secure containers, is really understanding what is in those containers. There's 2 gigabytes of executables, random processes, daemons, who knows what, that are running in the background, which inevitably open up your system for security breaches. Now, that sounds a bit dramatic, but let's take it back a notch because we don't have to make it dramatic, right? If I was to run some sort of container scanning tool on this image, it's going to come back with loads of critical vulnerabilities and it's going to be painful to deal with. But that's the wrong way to think of security. Security isn't something that you scan for necessarily or you run a tool in order to implement. Sometimes security is just knowing what it is you're doing. So let's take a step back together and let's know what it is we're doing with containers, so then we can build secure containers together. And we, at the end of this, will even make a very secure container for this one example project here. So let's just remind ourselves, what is a container? I realize this may be pedantic, but it's good to understand that we have a uniformed understanding of what's actually happening. So historically, what we would use is virtual machines, right? So the architecture would look a bit like this. You'd have down here the hypervisor. On top of the hypervisor, you would have all of your different virtual machines. And each one would have its own operating system, a whole complete operating system. Then on top of this, you would have all of the various dependencies that you would use. So we could say, deps. And then finally, at the very top, you would have your application. You'd have all of these layers of complexity when it came to deploying a virtual machine. Now, this is a bit different in the world of containers because the way that it works is you have your host operating system, which is Linux, usually. You have your container engine on top of that, which helps orchestrate the containers. And then on top of this, you have your containers. Now, what is a container? A container is just your dependencies, and then on top of that, your application. And the reason is because it fundamentally utilizes your host operating system in order to run. So this makes containers substantially more lightweight, especially when we start adding more and more containers and we scale up, right? We can utilize these shared configurations and shared resources in order to make scaling super simple and easy. So why is this important? Okay, you've just sold to me containers, but why is this relevant to, once again, making containers secure? Well, the fundamental reason is because most of the time, you already have all the dependencies you need to run your application already here. And this is something which a lot of people don't understand. And when you don't have something already down here, right, in the operating system layer, you just need to add the dependency you need for your applications. You don't have to add everything under the sun. You don't have to use these super generic container base layers to add everything you could possibly need when actually you only need the dependencies for your application. And so fundamentally, you need to figure out what that is. So once again, let's do some container building together, and then you'll be able to see really what I mean. So let's hop back to the code and let's have a look at this container. So let's think about this for a second. We make things more secure by reducing the amount of things in the container. The less dependencies we use, the less things there are in the system to be exploited and attacked. Just because something in your system isn't currently being used doesn't mean it's not an attack vector. For example, it may be that you have a very legitimate vulnerability in your application, which allows someone, for example, let's say, to gain access into the container. Now, it might be that they're restricted within that sense to only that specific node. And it could be that maybe something else you're running in the container allows them to jump between different nodes into the system and move laterally across the system. So you should never have the mindset of, well, that thing's unlikely to be exploited, when you can instead have a mindset of, well, that's not needed, let's just get rid of it. So let's start with some first good practices. So first things first, my recommendation is you create a dockerignore file. Because the first thing you should do to reduce files inside of your container is to actually think, hey, which things aren't meant to be in there in the first place? Now, this can all be just to reduce the size of the thing. So I encourage you to add things like the node modules, the outputs file, the output folder, .nuxt, the various different folders your application creates when you build it locally, because This will mean you're not having conflicts to your Docker build. But also just think, hey, what folders and files do I just fundamentally don't need inside of that container? Now, some of this may be just helpful for, like I said, reducing size, like the Docker file and the license file, but you may have whole folders in here which are fundamentally not needed inside of the container. And there may also be various commands specific to the build process for the tool you're using, which allows you to reduce the size of the final build. For example, with npm, you can do npm prune production to remove any of these test files which aren't necessarily needed in your production release. And now if we build these changes, we can now see that we have reduced the file from 1.8 gigabytes to 1.5 gigabytes. It's not a very impressive change, but it's a start. When it comes time to actually copying over your dependencies that you want to download, try to do it in a different layer. That's a good, fundamentally good habit to get into for helping you with caching. So by copying over the package JSON file, I can actually do the npm CI install before I copy over the rest of the files like so. Now, this won't actually change the build size of our container, but it's also important to think of containers like layers, because that's fundamentally what a container is when it caches it locally. It caches things in a series of layers, one on top of the other, and when you make a change because of file changes or whatever, it invalidates the appropriate layer and everything above it when it wants to rebuild the container. Now, that's just good hygiene. Now let's think about this for a moment. What can we actually do about this container? So the first easy answer is to actually give it a different base image. So if we go back into the image we made before, so I'm going to go into this one, I'm going to do docker run it entry point. So I'm going to override the entry point by default, so I can have a shell. I'm going to say the entry point will be bash. I'm going to run this image. And then we're going to see that if I go to OS release, that this is a Debian image. And by default, with a lot of these images, they use the fat version of these images. I say fat because the alternative is what we call the slim version, which has a lot of the fluff removed. But in these so-called fat or normal images, we have an extraordinary amount of dependencies installed. For example, if I have a look at everything on the root directory with a max depth of 1, I can see that we have 123 megabytes here in my application folder. You know, that's my thing. But I also have 75 megabytes under root. Don't know what that's for. I have 1.1 gigabytes of dependencies under the USR folder. And if we go into that, we can see that I have nearly 560 megabytes of library files. So this is a lot of stuff just shoved inside of this dependency layer below my application and completely unnecessary. So if we change the base image, it wouldn't have as much fluff there. Now, Alpine is a really interesting base image because Alpine only has, by default, I think 5 megabytes of dependencies. Now, obviously, the node Alpine image will have all of the node dependencies on top of that. But let's just give that a build and see what it comes out with. So it's going to have to build all the way from the beginning, invalidating all of our cache because we've changed the base image, meaning that every layer underneath has been invalidated. Now this is finished building, we can once again list all of our Docker images and we can see, wow, so we've just lost a whole gigabyte, right? Just one whole gigabyte has just vanished. And just to prove that everything still works, let's just run it again. So let's see if our web server still works. Look at that. So we have just obliterated one whole gigabyte from our image without fundamentally doing anything. Now, once again, I still haven't proven to you this is more secure, but just think about it for a second. From the first image we had, 1.3 gigabytes of binaries, of libraries, of all sorts has now been removed from this image. There is something to know about Alpine, is it uses different C libraries from normal Debian images. Instead of using glibc, it uses the muzzle images. Now, the details aren't very important, but fundamentally, if your application needs glibc, you should prefer a slimmed down base image which supports glibc. But we'll come back to that in a moment. Now, we can make this even smaller, but before we do that, let's take one step back for a moment and let's learn some fundamental concepts which are important before we proceed, right? So I have a very simple Golang application here. Very simply, all it does is just print hello world. Very simple. We have a Go mod, it's pretty empty, and I've made a very basic Docker file for it. What I'm doing is I'm building from the base Golang image. I'm setting my work directory just like we did with the previous one. I'm copying over the Go mod and Go sum files. Basically, they're the dependency files. And downloading any dependencies, there isn't any dependencies in this example. And we're copying over our files. Now, we can be more specific. That's always good from a security point of view to be more specific on actually what it is you need to copy over. And we're just running the standard go build command here. And I'm setting the entry point. Now, if we build this image, it's going to once again take a moment to download any dependencies it needs. And then we go over to see the sizes of the image. We can see that this image clocks in at 850 megabytes, quite large, which is weird when we think about it because Golang just makes a binary. So if we do that ourselves, we make that binary ourselves, we can see that the binary is only 2 megabytes. So once again, why is this 852 megabytes? That's a huge difference. Now, just remember what I showed you before over here. You know, our application should only have the dependencies it uses in production. Why am I running my application with 850 more megabytes of dependencies than it needs, right? This application here, 2 megabytes. The dependencies, 850 megabytes. Completely unnecessary, especially because we're building a binary. So you might be thinking, hey, we just learned a neat trick. Why don't we just change the base image? And we build it again. And you think, well, great, we just lost 500 megabytes of dependencies. That's amazing. But why do we even need all of the dependencies to build Golang projects in the actual release, right? Why can't the release just have our application in it? So let's do that. So what we can do is we can split our container into 2 parts. This is what's known as a multi-stage build. So I'm going to create one, which I'm going to call build time, and it's going to solely manage the building of the application. And the way that we signify that this is the building part is we say as, and then we give it a name. So from, as, and I'm going to give it the name builder. And then we can create a new stage called, for example, runtime. And instead of depending on a Golang base image, I'm just going to depend on the base image for Alpine itself, which remember, I told you was about 5 megabytes. And then we can copy from the other stage, just like this, the application. So we can do app main to, let's just say main. And then let's copy over the entry point, and I'm just going to take out that app bit there. So now when we build this, we should have a much smaller base image. So we see here it's 9.5 megabytes. So this is a huge reduction. We've just lost another 250 megabytes. And we can prove everything still works by just doing a Docker run, and we're getting the output of our Golang program, which just says hello world. I didn't demonstrate that before, but we can go even further. So what is Alpine? Alpine is what we consider a minimal distribution. However, there's a key word I use there, distribution. What is a Linux distribution? Well, a Linux distribution, usually you could think of it as a Linux operating system which has combined multiple dependencies together and usually added certain scripts or tools to make the operating system easier to manage. For example, with Debian or Ubuntu, we have the apt package manager. And with Fedora, for example, we have DNF and RPM. Alpine, being what we call a minimal distribution, also has its own package manager, which is APK. For example, if I go into Alpine here, I can say APK add curl, and it installs curl into that container. But hold on a second. Why do I need to be able to install binaries into my container that just needs to run my application? Well, we can go smaller than Alpine. We can use something called Scratch. So Scratch is a bare bones empty container that's doing nothing. And we're going to copy in the binary and we're going to run it. So let's build this new container. It built instantly. Do Docker images. And we can see my new container is 1.89 megabytes. It's literally the size of my binary. And we can prove everything still works. Hello world. So we have reduced this Golang container from 850 megabytes to less than 2. We have removed 850 megabytes. In short, if we think about this again, we have removed all of the dependencies underneath our application, right? So our application is just sitting on top of the container engine without any dependencies because it doesn't need any, and it's just humming along happily. And that's perfect because think of it this way. The attack vector has been greatly reduced. There's no dependencies on a container level that have to be updated and patched to ensure that our container is secure. Obviously, we'll still have to patch maybe the dependencies my Go application imports, and obviously we'll have to keep my Go application secure. Now, you may think, hey, that's great. Why don't I put everything into a Scratch container? And this is where security becomes really about understanding technology, because to me, that's what security is. Security, once again, isn't about just executing tools and scanning things. It's about really understanding what it is you're doing and why you're doing it. So why would we want to have a container with more dependencies, libraries, and configurations on it when we could just have Scratch and have just our application? So here's another example with Golang. So I have another application here, and it connects to some JSON placeholder website, which requires HTTPS. And it's going to read and give me the response here. Just fetch from this URL and print out the response. Now we'll build this, and let's quickly, once again, let's just quickly have a look at the image size. We can see it's 7 megabytes, which is a jump up, but the reason is partly because Go tends to create quite fat binaries, and that's really just because we're now importing these extra dependencies for Golang to operate the code. But when I go to run it, it won't work. So for example, I run it and I get this error message that it can't verify the certificate. The certificate is signed by an unknown authority. And the reason is because your dependencies, they're not just libraries, but they can also be CA files. So for example, your application is able to validate that an SSL certificate has been signed by a known authority. Now, you might think, okay, so I need to install into this container here, into this Scratch container, these certificates. But the problem is remember, there's nothing in this container. So there's no distribution to help you install those dependencies into it. So what we have to do is we have to go up to our build time container, obtain those dependencies, and then copy them across. So in this example, the dependencies is the CA certificates. So inside of the build time container, I'm telling it to update the CA certificates, which then gives me the ability to add an additional copy command to copy over the certificates that have been installed into this container into this one. So you see here, we're copying those over into the Scratch image just like this. And now if we build this container, we should be able to run the application and see the response here from the remote server. And obviously, as to be expected, it adds around 300 megabytes of files into our container. So when we're building our container, it's important to be thinking, what is actually required for my thing to run in production? I'm not saying you should always use a Scratch image and build it up, because that would be painful and arduous. However, sometimes it is exactly what you should be doing, depending on the binary you are deploying and how things should be secured. Now, here's an example of why it's important to understand your actual requirements, because in this example, I want to run this TensorFlow example application which just prints hello world. And in an attempt to make my image small and secure, I have depended on the Alpine version of the Python base image. And when I go to build this container, and we see here it's going to do run pip install, oh, it errors. Now, why does it error when it's trying to do pip install TensorFlow? Now, the reason is here, no matching distribution found for TensorFlow. Now, that's a bit confusing, but basically what it's saying is it can't find the pip for Alpine, specifically for Alpine. For example, if I change it to the slim version of this image, and we try to build it again, we should see that it works. And the reason is because the slim image is based on Debian. So why does it work for Debian and not for Alpine? And the reason is, as I kind of mentioned before, Debian has glibc dependencies, which TensorFlow in this example requires. Now, it might be that your application compiles fine for Alpine, but for some operations, it can take substantially longer. For example, I've seen with Rails and Ruby applications that sometimes the execution can take up to 4 times longer. Usually though, I think the difference can be unnoticeable, so I wouldn't be too concerned. But it is something to be aware of what your actual requirements are. And perhaps some benchmarking might be required for you to understand, hey, is the difference between glibc and muzzle actually noticeable for my application? So if we have a look at the size of this image, we can see it's 2.5 gigabytes. And really the main reason is because TensorFlow is huge. But obviously, because we're using the slim version here, there will be a lot of dependencies that we have that we don't use. Because if I recall correctly, the slim version for Debian usually starts at around 120 megabytes as it is. But that means 2.3 gigabytes is still being taken up by TensorFlow. We should be able to run our application, and we can see here that it works just fine. Not all hope is lost, right? So we've found out in this example, it doesn't support Alpine. So how do we actually make it smaller? Now there's a series of container base images, which we call distroless, and it's a project by Google to be able to provide base images which are compatible for a specific language, but they remove unnecessary fluff inside of those images. So these are still going to be bigger than, say, an Alpine image or a Scratch image, but they will have a lot of unnecessary stuff removed. For example, just like with Scratch, you will not have a shell or the ability to download dependencies through a package manager. And if we go to their examples, we can find an example here for Python 3 requirements, and we can see here that they have an example on how to run a Python application which has a requirement. So in our example, it does have a requirement, which is TensorFlow. So I've copied over the example and I've made some basic changes. We can see here that I install all the dependencies as it suggests. Basically, what we're doing here is we're creating a virtual environment for Python. We're going to install all the dependencies into that virtual environment, and then we're going to copy over the virtual environment into our runtime container, just like we are here. Then we can copy over the application, just like I'm doing here, and then run the application from the binary inside of the virtual environment. And if we build this, you'll have quite a lot of dependencies to download from here, because just to make sure you've noticed, we're using a different base image here. We're just using the standard Debian here. We're not actually using a Python base image here. And also, as it's downloading, you can see here, we're also removing everything unnecessary from that virtual environment here. And that's always a good mindset to have whenever you're building these containers. Remove everything that's not necessary. You don't have to copy over, like for example here, if there's any PyCache files like this, let's find them and remove them from the virtual environment to keep it as small and as lightweight as possible. So you may see here that we're depending on the Debian 12 version of the Python 3 distroless base image. And the reason why we've specifically said Debian 12 is because this is the image which Google has automatically added in the glibc libraries for us. And we should be able to run this new image just like before, and it works as we see here. And we see we've knocked out 500 megabytes from this image. Right, so now I have this C application here. It's very simple. All it does is it tells me which the current username and user ID of the currently logged in person is, and whether or not it can write to both the root directory and the app directory. It's going to try to create a file in both directories and just let me know if it has permission. So I'm going to create a Docker image, and for the build time, I am just installing the various dependencies needed. I think a lot of these probably are already in there, but I just added them anyway. We're going to copy over our C application, and we're going to build it. And then in the runtime, we're just going to copy it over from the builder and execute it, and make sure we make the app folder, because we're going to test if we can run stuff in that folder. So while I'm building this, let's talk about this for a second. So we've talked about reducing container sizes for security purposes. But the next point for security is actually thinking, what user is my application running as inside of this container, and what permissions does it have to do things? So by default, nearly every base container for various languages always let you run as root, which means you have full permissions over that container. So we can see here, inside of this container, I'm running as root, username root, user ID 0, and I can create files inside of my app directory and also on the root. Now, often you will want to give your application permission to be able to add, mutate whatever files inside of its own directory. And usually you don't want it to have permissions to be able to mutate, add, or remove files in the root directory, because that obviously can have unintended consequences. For example, maybe someone overriding a binary inside of your container through your application, allowing him to maybe move laterally or commit some other type of attack. So why don't we actually lock down my application so it only has access to the app folder? So what I'm doing here is I'm creating a new group and a new user inside of my container called app. And I'm modifying the app folder to allow the app user and app group to be able to own this folder. So let's say I build this again. We can see here that I'm registered as user ID 999, username app, and I can successfully write to the app folder, but I'm not allowed to write to the root folder. But once again, if we go to look at our image, we can see it's around 75 megabytes, which is huge for a tiny C application. So you might be thinking, okay, let's reduce the size by making it a distroless image, just like you showed us. So we swap it over to a distroless image, and then we try and build. And when we build, we'll see these errors, which basically say that it can't find bin sh. And remember what I said about distroless images, they don't have a shell, they don't have a package manager, they're bare bones. And so we can't do all of this fancy pants, make dir, create a user, show in a directory. We can't do that. We have to remove that from the runtime, meaning we have to handle this logic as early as possible, for example, in the build time. So what we can do is we can make our folder all the way back up here inside of the build time. And then inside of the runtime, we can just copy over this folder like so. So now if we go to build it, we should be able to run the application. And we see here that unfortunately it has access to everything because we have removed the ability to lock it down. But if we go over to Docker images, we can see we've reduced it from 75 to 23 megabytes. But the fact of the matter is we want to lock it down. Now, the distroless containers have a non-root alternative version of them. And if we try and run this now, we should now see we're running as user ID 65,000. And I think that's the actual highest user ID, maybe a few less than you can actually have. We can see here we have neither permission to the app folder or the root directory. So we've lost all permission. That's not what we wanted. We wanted to keep permission to the app folder. But we do know now that our username is non-root. So what we can do is when we copy over this app folder, we can chown it. And we can say when it's being copied over, what user ID and group ID the folder should have. So if we build this again, we can see that we're running as non-root. We can create the file inside of the app folder, but we can't modify the root folder. And once again, we should continue to have our smaller image at 23 megabytes. Now, if we think for a second, why is it even 23 megabytes? Because if I build this binary locally and I have a look at the size, we can see it's only 17K. Now, obviously the distroless images have more inside of them than the scratch image I showed you before, but it's still absurd we got to 23 megabytes. So this image here is adding the dependencies to allow you to also build C programmers. So if I just change this to the base Debian image, we should find we get a result even smaller. So we can see everything still works here as expected. And if I go over to Docker images, I can see the new one here, and we've reduced it to 20 megabytes. So we've knocked out about 3 megabytes of dependencies to be able to build the image. So now we've gone through all of these different examples, we can come back to our original Nuxt image and start implementing some of the things we learned. So if we have a look at our Docker file from before, we can see there's a lot of cool stuff we can do here, right? All of these things we've learned. So obviously the first thing we could do is probably split it off into two separate stages, right? Just like we did with the other images. So if we put it into two different stages, we can have a different one for the build time and the runtime. So we're only copying over the compiled JavaScript output. And we're not going to copy over our source code or the node modules, for example. So if we build this, we can see that the previous one was 500 megabytes and our new one is 163 megabytes by just splitting it into two different stages. But as you know, we can go even further. So just like before, why don't we swap the runtime image to being a distroless version of itself? So let's try and build this. And now we can see we've knocked out another 20 megabytes of dependencies. So I've got it down to 144 megabytes. And that's probably because we're getting quite close to the actual size of our JavaScript files in the output folder. And now we've removed all of the unnecessary dependencies inside of this container, why don't we now secure it and lock it down so our main application can't access or mutate files outside of the output folder? So as you see here, I'm doing as non-root and we're choning the output like this. So we should be able to go back here and we see that with these changes, all of these changes, everything still works with the Nuxt, the node application. Everything just works fine. So just to reiterate, if you remember where we came from with the Nuxt image, we came from 2 gigabytes and we've reduced it all the way down to 144 megabytes, removing the ability to exec into it. So for example, if we wanted to open up a shell, then we'd get an error message saying that this container doesn't have a shell. So we can't run commands inside of it. So we can't do silly things to it. We can't ls, we can't rm, we can't touch, right? This container is, for the most part, pretty locked down. Now, obviously, there's more things you can do to lock down a container in the run stage, but I'm focusing more on the security side of a container in the build stage in this specific video. So now we only have one application left that I actually want to show you. Here's another example. Let's say, for whatever reason, we had an application which wanted a secret on build. So in this example here, I have a C application which is looking for API key to be defined, so we can override it inside of the application like a variable. But a better example might be, for example, let's say you had a node application and you wanted to do npm install, but you had to have a secret inside of the container while it was installing to be able to fetch the dependency from the remote server. How do we actually secure that? One way that you could handle this is just to copy in the key into the container, just like this. And let's do that. So let's do docker build. And now when we do docker run, just to show what it does, we should now see it saying using API key hello, which comes from this file here. And that's baked into the build. It doesn't use that on runtime. And we can prove that by obviously just changing the file and see that it's baked into the build. The problem with doing that is we have baked it into the build. For example, let's say I do docker run entry point equals bin sh 6 secret 1. We have to make it interactive. We will be able to see the file inside of the container in plain text. So this is insecure, right? Because anyone who has permissions to pull the image will subsequently gain this API key, right? What we actually want to do is to not keep this API key inside of this container. Now, what a lot of people will do to resolve this is they will run a command afterwards, which just deletes it, right? But you're still storing this inside of the layers, right? So if someone was able to stop the build process at a certain point or whatever, they would be able to see inside of the layers the files there. And also, this is kind of dirty. We can do it a lot neater and a lot nicer than this. So let's remove both of these lines. So what I've done here is I've said I'm going to mount a secret API key. And then I'm going to run this shell command here. And I've done this a bit hackly just because the way that I'm importing the secret is a bit weird. You normally wouldn't cat this. Like I said, normally you'd be using the file for something else. But just for demonstration purposes, I'm just catting the file under run secrets API key into the build process here. So that's why it's in a subshell. And now if we were to build this and then do a run, we should see that we can't actually access this secret in the built container. It doesn't actually exist. but the application should still work. Now, when we go to build this, it will be a bit different. We don't just do docker build. We actually have to specify where on the operating system this API key file is. And we do that by specifying -- secret, set the source to API key. So we're saying, the API, the ID here, as we're matching to this, and we're pointing it to this file here, which is the name of the file there. So now when we build this, we can see that we've got the API key working as expected. And obviously, if we exec into this machine here, we can also check that this secret isn't actually inside of the machine. So it's all been cleared up for us. And obviously, to reinforce everything, we can copy everything we have here into a runtime image, which actually is the thing which runs to keep it lightweight. So obviously, we can see here we've reduced it from 200 to 24 megabytes, 250 to 24. So you can see here we've continuously been able to shrink images through things like multi-stage builds, but also really thinking, hey, what is it my application actually needs for production in order to run? Now, you might be thinking, all right, that's nice and all, but I don't entirely trust you that this is good for security, right? I mean, it sounds nice, lower number, but where's the proof that this is actually good for security? So let's introduce these scanning tools to prove our methodology, right? So I'm going to make two folders. One's called Trivy Cache and one's called Trivy Workspace. I'm going to go into my Trivy Workspace folder, and what I'm going to do, I'm going to save various images that we've created as a tar file. So we'll be able to easily determine whether or not we have had an impact from a security perspective on these containers. So I'm going to save a few of these. I've saved a few of the files here. I haven't done a complete set because obviously this would take forever to go through. But let's just have a quick look at a few of these here. So let's see how many vulnerabilities we had right at the beginning from the Nuxt image we first created all the way at the beginning, which we just used the standard basic node image. I think it was the latest one too. Let's see how many vulnerabilities we actually got. So in order to do this, I'm going to run the Trivy container. Trivy is a tool to be able to scan containers for vulnerabilities. I'm going to cache the output of this into my cache folder so I can keep rerunning it. And I'm actually only going to filter to high and critical. And I'm going to point to my image for the first one there. So it's going to take a moment to pull. So let's have a look here. So it is showing me all of these different dependencies, and it's showing me how many things are critical or high. And I've only filtered critical and high, right? Because if I had other vulnerabilities here, this would go on even longer. We can see all of these different CVEs that are showing me. So a CVE is a common vulnerabilities and exposure. And basically what it is, if we go into one randomly, is it's a description of a known vulnerability. So this one's only considered moderate here, but it has a 7. Usually anything 7 or up for a lot of companies is considered something that has to be dealt with, and it will explain the vulnerability here. The problem with CVEs, even if you think you're not vulnerable, you always have to go through them and determine whether or not you're vulnerable or not. Sometimes it can be hard to figure out from a quick look whether or not you are vulnerable. So for example, in this one, it's talking about the Linux kernel. This is getting technical. This is something I'd actually have to think about and read up on to think whether or not I was vulnerable. And that's the problem with CVEs in general. They're really nice to see, but determining which ones are valid and which ones are not is work, a lot of work. Now, just scrolling up through a list of vulnerabilities is kind of useless to gain the scope of what's actually there. So I have this other command here, which is just going to summarize the results. And we can see here when I do that, I have 8 critical vulnerabilities and 159 high vulnerabilities. So that may not mean my application is actually vulnerable, but these are things I have to be concerned about when I'm securing my system. So let's jump forward a bit to when I split it off between my main application and a multi-stage build. We can see here already, it isn't even coming up with anything as it is. So that's already a huge improvement, right? We can also have a look where we came from with the Golang first example by shoving that in there. And we can see the first example, we had 3 critical vulnerabilities and 133 high vulnerabilities. And just to remind you, that's when we were using the normal Golang base layer. And then we can look again as we change it to Alpine, and we see we have no critical and no high vulnerabilities. If I wanted to, I could then inspect this even further and have a look if there's any low vulnerabilities. And as I see here, there is 2 known low vulnerabilities for when we split this into an Alpine image, right? But we went further with this image. We turned it into a Scratch image. So let's have a look at the Scratch version. And as we see here, the Scratch version has no critical and no high. And let's just have a look if there's any known vulnerabilities. And of course, there's no known vulnerabilities in the Scratch version because the Scratch version was literally empty, right? It only had an application in it. So there was no known vulnerabilities in the Scratch version of this application, which is amazing. That obviously, just to highlight, that doesn't mean our application didn't have any vulnerabilities. It's that there was no known vulnerabilities in the dependencies of that specific container, right? So it's very easy for us to determine whether or not our application is secure by just thinking of security from now on in the context of our application, or alternatively in the context of the dependencies, like the package dependencies, like the Golang dependencies that our application actually uses. And then finally, we can repeat the example for the non-root container that we made. And we see it has 0 critical and 0 high. I fully expect this to probably have a few more known vulnerabilities than the Scratch version, just because it was distroless, so it's still doing something. So it still had some dependencies. And we see here there's a small collection, but only one of them is considered medium, something to do with SSL, which we could obviously update. Hopefully Google releases a new version of the distroless image. So I hope that's pragmatically shown you that when it comes to security, it's not about implementing the tools first, because if we implemented the tools first, so let's go back to us scanning the first container here. These are all the vulnerabilities we have, right? The known CVEs. If we implemented tools first, we would be here forever because we would be like, we need to now patch this thing here, or we need to patch this thing here. And you're in an endless game of fighting vulnerabilities through patching. And the downside of fighting vulnerabilities through patching is a few things. Patching takes time. Patching can break applications. It's honestly just boring and nightmarish. And it's instead better to secure something by knowing how it works and by knowing what is actually required for your thing to actually run and operate. Because, like I was saying, if you started to secure something by going through this list, you would be here for weeks. It's far better to do it by actually rethinking what it is you're doing and how you're doing it. I hope you guys learned quite a lot in this video. I hope this was really in-depth and has really given you an understanding on how to actually secure your Docker containers. If you need any help with managing your containers in your organization, then feel free to reach out to us. We will always be happy to help and give you expert guidance and advice. We're currently working on a white paper, which you'll be able to sign up for, which will give you key insights on how to secure your clusters for a remote-first organization. So organizations where you have developers scattered all over the world, how do you ensure that their development workflows are secure and their releases are secure? Thank you so much for checking out this video. And as always, I hope you guys have a lovely day. Cheers.